Hello and welcome to your lesson on ice charts, also called ice tables or ice boxes. This is one of the most difficult things in the course, but if you go through it in a systematic way, it's not so bad. Today is actually a pretty short lesson in terms of like notes and material. Most of our time is going to be spent going through 3 examples because these are pretty complex. So first of all, what is this? What are we doing when we do ice charts or ice tables? Well, what we're doing is we're either solving for a concentration or we're solving for an equilibrium constant. Now we're going to be considering 2 sets of concentrations. Initial concentrations, which is the I in ice, and then the equilibrium concentrations, which is the E. From the initial and the equilibrium, I can also figure out the change. And those changes can relate from one chemical to another chemical by using the molar ratio, kind of like stoichiometry. So what I'm doing in an ice chart, what the problem is asking me is to either to find a concentration initially, so that's before equilibrium was established, what was first put into the reaction vessel, or to find a concentration at equilibrium, or alternatively to find an equilibrium constant, and I'm missing some information. Okay, so I've got maybe some I concentrations or some E concentrations, but not all of the E concentrations in that case. So what we do is we track info for concentration before and at equilibrium. We relate it because of the change between initial and equilibrium concentrations. And then using molar ratios, we can find the change for other chemicals to solve for stuff. But you're going to see it. It's going to all make sense once we actually get into the work for this. If what I said so far is just way out there, we'll get there. It will all make sense with the examples. So to build the chart, we put down at the top every single chemical that is involved in the Kc expression. And then we put down I, meaning initial concentration, C, meaning change in concentration, it's positive or negative, up or down, and then E, meaning concentration at equilibrium. Use ice charts only if the question says something about initial. So there has to be initial and equilibrium concentration information there. If it just talks about equilibrium, this is easy. This is just a Kc expression, right? You're just plugging in to find Kc, or you're using Kc to find equilibrium. So only use this if it says something about initial concentration. If there's no word of initial or starting or any information from before equilibrium was reached, you are not using ice charts. It is a simple plug stuff into the equilibrium expression, use the Kc value to find the concentration. All right, so what you're going to do is you're first going to write out your equilibrium expression, right, which is equal to Kc. You're going to build your ice chart and solve for everything you can. Sometimes you have to use X's for changes, for example, because you don't have enough information to solve. That's rare, but it happens for the really difficult questions. And then from there, you're going to sub into the equilibrium expression and use that to solve the problem if you haven't already solved it after step 3, or step 2, I should say, of using this ice chart. So here we have an example. We're going to work through it together. Hopefully this will make sense. And we're going to do 3 examples. So first one we'll do together, and then 2 and 3, it's good to pause. Okay, try it out and then see how you're doing. So reaction vessel was filled with nitrogen dioxide gas to a concentration of 2 moles per liter. At equilibrium, it is found that there is 0.250 moles per liter of nitrogen monoxide. Calculate Kc for the following equilibrium expression. All right. So this doesn't actually say right off the bat anything about initial, but it does kind of say like it was filled with NO2 to this concentration, and then we had equilibrium. So even though it's not explicitly saying initial, this implies that there was a before equilibrium was reached and then an after. So because of that, I'm using a nice chart. So my Kc, that's my first step, is writing out my equilibrium expression. will be equal to concentration of NO2 gas, which is squared because I have a coefficient of 2, divided by NO gas, which is squared, and O2 gas, which is to the power of 1. So products over my reactants. So now here's the information that I have from my question. It was first filled with NO2 gas. So I have my ice chart here, initial change, equilibrium, and then I have all of my chemicals that are involved in my equilibrium expression. So NO, O2, and NO2. So for nitrogen dioxide, I have an initial concentration of 2.00 moles per liter. I'm not going to write units because I don't use units in my Kc expression. I then know that because of the absence of information here, it doesn't say anything about there being NO or O2 to begin with. I'm going to make an assumption, and I do this a lot when it comes to initial, that if it doesn't explicitly say that I have that stuff to begin with, that this is going to be a 0. So I started with none of this. I only had NO2 to begin. At equilibrium, it is found that there is 0.250 moles per liter of NO. So this is 0.250. Okay, that's all the information I have from the question, but I've now got a sandwich here and I can find the filling. I have 2 moles to begin with, moles per liter. I have 0.250 moles per liter at the end. So that means that I had a change of negative 1.75 moles per liter. So it went down by 1.75 to reach this. NO2 is on the opposite side of NO and O2. So if this went down, if I used this up, then these two had to increase. And they increase according to their molar ratios, their coefficients. So if NO2 with a coefficient of 2 went down by 1.75, how much do you think NO is going to go up by? And the answer is positive 1.75. So what I've done here is just said 1.75 times 2 over 2, yeah? Because it's 2 over 2. Now, if I had O2 with a 1 and NO2 with a 2, well, what's the difference there between those? And that would give me an answer of, at the end of the day, 0. plus 0.8, I'm struggling on this, 75. I actually have to check that on my calculator, which I feel silly about, but I don't want to mess up this video. Yeah, okay, I was right. Oh, self-doubt. Jeez. Next, I have equilibrium, so I can now take this, add this, and find this. So I have 1.75 right here, and then I finally have 0.875 right here. So now I have all the information that I could possibly need to find my Kc. I'm going to go back up to this, so erase that little work there, and I'm now going to plug in my stuff in order to solve. So I have 0.250 squared divided by 1.75 squared and 0.875. So in my calculator, I'm now going to go ahead and plug in this information. So I have 0.250 squared divided by, in brackets, 1.75 squared and 0.875. Close those brackets, press enter, and I end up having a value of 0.0233. Just going to double check what I had plugged into my calculator to make sure I didn't make a mistake there. Looks good. Looks solid. So that's number one. So not too bad, right? The big thing is remembering that when I look at the change right? As soon as I have this sandwich, I have initial and equilibrium, I can find a change, and then I can relate this change to other changes using the molar ratio, realizing that things on the same side of the equilibrium will go in the same direction, right? Either plus or minus. And then things on the opposite side of the change I know will have the opposite sign, which makes sense. If products go up, reactants have to go down and vice versa. All right, let's move on to the next question and give it a go. A certain amount of NO2, same reaction here, which is nice, handy, was placed into a 5-liter flask. Ooh, added complexity of a mole per liter calculation. At equilibrium, NO gas equals 0.800 moles per liter. Given that Kc is equal to 24.0, we must have changed temperature because now we have a different Kc. Find the amount in moles of NO2 gas initially placed in the vessel. Okay, so why don't you start out by trying to fill out your ice charts. So you already have the equilibrium expression from the last question. It's just simply Kc is equal to, and I'm just going to recopy it out here, might as well, NO2 gas squared divided by NO gas squared and O2 gas. Okay, so take a quick moment and put in everything that you can find from the question into your ice chart, and then take a look and see how you've done. So, certain amount of NO2 gas was placed into a 5-liter flask. I don't know what that is. I'm just going to put a little question mark there for right now just to keep track of the fact that that's kind of what I don't know. At equilibrium, now, something I do know is if I put in NO2, I can assume that O2 and NO I had none of, right? So whenever I have absence of information for initial and it's like, oh, you put in this thing, well, then I can assume that I didn't have the other thing. So I have no NO and I have no O2 to begin with. At equilibrium, my NO was 0.800 moles per liter. Now I've made a sandwich, I can find that filling. And I know my Kc is equal to 24.0. Hooray! So now in terms of information, I know that I've got positive 0.800 right here. If I have positive 0.800, then for O2, given that it's a 1 to 2 ratio, this must be positive 0.400. And given that NO2 is on the other side but has the same number as NO, this must be down 0.800. Okay, so that's where we're at right now in terms of information. I know that then for O2, I have 0.400, so I've got that. So that means that I can actually go ahead and try to solve for this as an x. So in other words, what I have is that x squared over 0.800 squared multiplied by 0.400 is equal to 24. So now I can do some algebra and I can solve for that x. So let's first of all figure out what that denominator works out to. So 0.80 squared multiplied by 0.4 means that I have 0.256. So right now, and I know a little bit ugly in terms of how this is showing up on the page. Try to look past that. I'm going to change the color. I'm worried this isn't showing up as well as other colors could. I have 24.0 is equal to x squared over 0.256. So now if I multiply both sides by 0.256, right? So multiplied by 0.256, multiplied by 0.256, and then I take the square root of both sides, then I will have my answer for x. So I know I'd like to show more work here to show the process, but I'm a little bit out of space and I feel like starting a new page would actually make this worse. So let's go ahead and plug this into the calculator and try to follow along. So 0.256 multiplied by, just made a star on the page, don't want that, multiplied by 24.0 gives me 6.144, and then I'm going to square root that and end up with an answer of 2.48. So that means that at the end of the day, my x is equal to 2.4787. Okay, what I think is good to do now, what I like doing at this point, is actually taking that and squaring it and dividing it by 0.80 squared. And then I'm going to multiply that by 0.4, put all of that in brackets, which I should have done to begin with here, but I did not. And just make sure that that's coming out to 24, which it does. So I know that this value is good because it came out to the Kc value that I already knew. Well, I'm not done yet. Now I need to find this, my initial concentration. So this is after 0.800 was subtracted from it. So if I want to find this value, I have to add 0.800. So that means it's going to get me 3.2787 for a concentration for initial after I've added this to get my initial. So that's the concentration that I had before it was placed in my vessel. But I need to find the number of moles of NO2. So last step is doing a little bit of N is equal to CV, where I take my 3.2787 moles per liter, multiply that by the 5.00 liters I've got. Oh, made the star again. Multiplied by 5, and I end up with an answer of 120 moles. Ooh, that's a lot of moles. Oh, no, wait, whoa, that was a mistake. Did not have the right number there in my calculator. That could have been bad. Times 5, there's a better answer. N is equal to, and I want this in 3 sig digs, 16.4 moles at the end of the day. So that's what I get for a final answer is 16.4 moles. All right, that's number 2. That was a tougher one. Are you ready for the next level? Here is a different equilibrium, number 3, little bit more complex. Let's give this a try. So start out, why don't you write out the equilibrium expression for this sucker and then check your answer and see how you done. So here I've got Kc is equal to xy gas to the power of 2 divided by x squared. Nope, no, not squared, x2 and y2 on the bottom of that equilibrium expression. And I know that Kc is equal to 15.0. That's given to me. I also have initial concentration for x2 and y2, which is great. And I'm going to try to figure out the equilibrium xy. This is going to be an intense algebra question. We're going to have to make a new page to work through all of the beauty of this math. Now that we've got this equilibrium expression, why don't you try out the ice charts, write down everything that you can find from the question or figure out and see how you've done. So here's the information I've got. I've got the initial of 0.200 and 0.200. XY is not mentioned, so I'm going to assume that this started out as being a big old 0. I did not have any of that in my initial vessel. Hopefully you're seeing this trend that when I have absent information for initial, when it doesn't say I had any of it at initial, I'm going to assume it's a 0 for that. So now that I've got that information, let's do some X's for the change. So I'm going to have x2 and y2 go down. They can't go up because I don't have any xy on this product side to go to the left to make them go up. The only thing I have is x2 and y2 to turn into product, to go towards xy. So I'm going to have this go down by x for x2. Given my coefficients, if x2 goes down by some amount x, y2 goes down by the exact same amount because it has the same coefficients. Now, how much does xy go up by then, given the coefficients? Well, it goes up by 2x. So that means I have, for equilibrium, 2x. This is 0.200 minus x. and this is 0.200 minus x. So all I've done is I've taken the change, right, and put these together to express equilibrium as, an expression. So now what I can do is I can plug this beauty into here and say, well, I now have 2x squared divided by 0.200 minus x for x2 and 0.200 minus x for y2. Okay, so now we get into this beautiful, beautiful math to solve for x. X isn't the answer to the problem. What I'm trying to find is the equilibrium xy. So once I find x, I have to multiply it by 2 to actually find that equilibrium concentration. But that's the steps I have to take. So now that I've got this expression, let's now maybe make a new page and dive into the math. Let me, first of all, just snag this right here. Yeah, gonna snag it. Snagged. Go to here, Control V, boom. And that was equal to, if I remember, 15.0. Yes, 15.0. 15.0. All right, beauty. We're in business. 15.0. If I have this squared, and I have 0.200 minus x twice here being multiplied together, then I could say that this is equivalent to having 2x, and this is all squared, over 0.200 minus x squared. Yeah? This is the same as if I had 2x over 0.200 minus x, everything squared. That would be equivalent as well. So now that I know that, I can get rid of this squared by square rooting 15.0, so square rooting both sides, and saying that's equal to 2x over 0.200 minus x. So now I need to get all of my x's together on one side and everything else on the other. So I'm going to move this binomial up to the top. So in other words, I'm multiplying both sides by 0.200 minus x, that binomial, in order to get that worked out, right? So what I've got then is square root of 15.0 multiplied by 0.200 minus x is equal to 2x. So now let's actually find some numbers for this, and then we can move the x terms to over here. So if I take the square root of 15, right, so second square root of 15, I get an answer of 3.873 is a good place to round it at. So 3.873 multiplied by 0.200 minus 3.873x. So square root of 15 is multiplied by 0.200, and it's multiplied by the x, and I get that term. And that's equal to 2x. So let's now add this 3.873x to both sides, right, to get all of the x's in 1 point. And I end up with, I'm going to multiply this by 0.2, and do that now. I end up with 0.7746 is equal to 5.873x. So now I'm going to divide both sides by 5.873. I'm also going to close Hangout so it doesn't keep on making that noise on you. And I'll end up with x is equal to, after I divide that by 5.8729833, 0.13189. So that's my x value. So that is x. If I go back to here, right, then it does make sense for x because at least that's less than 0.2. If I found a value higher than 0.2, it would make no sense. So now in terms of what this value would be, I would just multiply that by 2. So let's just round this to 0.132. And I end up with 0.264, right? So if I go back here, this is 0.264. And then I had 0.132. So this would be equal to 0.068 and 0.068. Why I'm doing this is I just want to plug in this stuff to make sure that my Kc equals out to 15 with the equilibrium expression, because I always want to double check my answer once I'm done to make sure that I've got the answer right, to be confident with what I have. So 0.264, I'm going to square that. I'm going to divide that by 0.068 and 0.068. I could have squared that, obviously, but I did not. And that ends up with 15.07, really close. So I'm good. I got it. I got the right answer. 0.264 is my final answer for the equilibrium K, or XY, sorry. So 0.264 moles per liter, final answer for that one, and I'm all set. So ice charts, are they tough? Yeah, they're super tough. Gotta involve a lot of math here. They get pretty crazy. Most of the questions you'd run into end up not involving X. It's kind of more like example 1 or 2 where you can solve it through the ice chart and figure stuff out. But these ones are out there. As a note, you will never have to use the quadratic formula in order to actually solve for an X. So this one, could I have used the quadratic formula? I could have, but you're not going to have to do that in Chem 30. There's always going to be a way to figure it out algebraically without plugging it into that monstrosity. What else to tell you? Yeah, it's tough. Remember that we're only using ice charts when it talks about an initial set of you're putting something into a vessel, you're beginning with something, and then equilibrium concentration. So you have 2 set of concentrations, and then you can relate them with the change. And then from one change, you can find other changes by using the molar ratios and understanding that if one side goes up, the other side is going down. All right, that's ice charts. Hopefully that made sense, and have a good rest of your day.